this module, we're going to talk about some microscope parameters that affect image quality and image presentation. So the first thing I want to talk about is brightness. So brightness, all it does is really refer to the intensity of the light. So it's a pretty simple, straightforward thing to think about, but just intensity of light. And so when we think about forming an image, and we talked about this in some of the previous modules, so if we want to make something visible, we don't necessarily just need high magnification. We also need to have sufficient brightness or intensity of the light to be able to visualize something. And so brightness is going to be related to the numerical aperture. So you saw that as NA, and that's raised to the power of 4 over the magnification squared. So the kind of takeaways and what I wanted you to get from this equation here is that brightness will go down if we increase the magnification. So basically if this goes up, overall it's going to go down. And we can also increase the brightness if we increase numerical aperture. So those are kind of the big takeaways from this expression. All right, next I want to talk about contrast. So contrast and brightness are often described together. And so this refers to the relative change in light intensity. So here we describe light intensity as a capital I. And so we're talking about the relative change in intensity between an object, so the thing of interest, and its background. So these are any sort of neighboring features. So we can describe contrast as an equation, and that equation is contrast equals the intensity of the object, so I'm going to just abbreviate that with the sub OBJ for object, minus the intensity of the background, and just back to represent background, over the intensity of the background. So I sub back again. So we need a certain level of contrast to be able to visualize an object. And so typically we think of them as sort of thresholds, contrast thresholds. And so if we have bright light, oh, sorry, I realize you can't see that. So with contrast thresholds, if we have bright light, then this can be as low as 3% contrast difference, right? So if something's well lit, then the contrast level is a lot lower. And this should be kind of maybe intuitive from the way you visualize things, right? At night versus day. And then if we have dim light, then this could be as high as 200%. So there's a huge difference here in terms of the lighting. So contrast, brightness, that's why you always hear those connected, because there's very much connection between those two. All right, the next parameter I want to talk about is depth of field. And this term, you might have heard of it in other contexts as well, but what this is it's a range of positions on the specimen we typically think of this as the z-axis because we're talking about vertically. So if we're looking at the specimen, you know, up or down from it on that. And so this is a range of z positions over which the sharpness, and so when we talk about sharpness, we're talking about, you know, the image quality. Can we see it? Is it sharp and in focus? And this does not change. Or we can also put it in another way. The specimen remains in focus. So that's what we mean by depth of field. It's a range of z values over which the image is still in focus. All right, so let me kind of draw you a sketch of this so you can kind of get a feel for what I'm talking about. All right, so I'm going to draw the aperture of the microscope. So this is where light's coming out. And actually, let me draw that again. Let me draw a bigger aperture just for ease of this drawing. All right, so this is the aperture. So this is our aperture. And this is where light's coming off. We are going to call this A to start with, the opening. And we're going to have light come out. And it crosses over, right? So this is the convergence point here. And so we call this our focal plane. So this is where the image is in focus. A couple other things to consider. If we make a normal to that, then this angle here is alpha, right? Alpha was the aperture angle, right? So we talked about that before. So that's the angle of that. And so the idea with depth of field is that the image is in focus in the focal plane. So that's the case. But we also talked about the limits of resolution because of diffraction, right? So diffraction kind of limits what we have there. So in actuality, though, there's a range. So maybe from here up to here. So this is our, and just to be clear, this is our z-axis. So there's a range of positions, and we're going to call that d sub f for depth of field. Right? So this is the range of z positions over which the image remains sharp, right? And it's sharp because of those limitations of resolution, it doesn't matter if we get exactly in the focal plane, but there is a little bit of wiggle room. So I'm drawing this to kind of exacerbate everything. So, you know, this depth of field is not a huge depth. I'm just kind of drawing it that way so that you can see the point I have here. Okay, so we can look at depth of field, d sub f, as a function of the resolution, right? R, that was the diffraction limit, over the tangent of alpha. So the depth of field is going to depend on the aperture and therefore the aperture angle that we're using. So this is one way of writing it, but we can also write it as 1.22 lambda over mu sine theta tangent theta. So this incorporates our definition that we talked about last time when we looked at R. So we're basically subbing in the definition for R, and also keep in mind that numerical aperture is equal to that refractive index times sine alpha. And so we can always kind of plug that in this case. So if we know the numerical aperture and we know the refractive index, we can also always solve for alpha and plug it back into this tangent alpha expression. So even if, in a problem, for example, if alpha isn't explicitly given to you, if you can determine the numerical aperture, you can find this depth of field. So that's important to keep in mind for future problems. Another thing I want to sort of you to take away from this as we first look at this expression is that if we compare this depth of field and resolution, what we'll find is that we cannot simultaneously achieve a high resolution and a high depth of field, right? High resolution means this is small, and so we can't make depth of field large and have a high resolution, right? So that's kind of the give and take we have with depth of field and resolution when we talk about light microscopy. We can reduce alpha, but that to increase, we can reduce alpha to increase depth of field, but that lowers the numerical aperture in A and therefore R. And so there's a give and take here that we have with this. All right, just a couple other points I want to make before we wrap up here with this module is just some estimates or quick references. So typically alpha is 45 degrees. So it's approximately 45 degrees. If you're just wanting some quick estimates, alpha tends to be about 45 degrees. And also the depth of field is typically about double the resolution, R. So that kind of gives you a quick estimate of those two quantities. All right, another thing I want to mention just here right at the end is we have dF, which is our depth of field. So you may have heard this term depth of field. You may have also heard the term depth of focus. These are not the same quantities. So these two are not the same. So that's just important to, so I'll try to be very specific when I talk about this quantity, talking about the depth of field and not depth of focus.